In this video, we are going to discuss the path independence theorem in vector calculus. So the theorem states the following. The line integral of f along C is path independent in D, where D is the domain of f, if and only if the line integral of f along C is equal to 0 for any closed curve C in D. So this is what the theorem states. Now we are going to prove this theorem. So this is a double implication theorem. So we are going to start the proof with the forward implication. We start the proof with the forward implication, meaning that we are going to start the theorem by assuming that the line integral of f is path independent in its domain D. So let's suppose this. Suppose that the line integral of f is path independent. Suppose that the line integral of f along C is path independent in D. Okay? So what does this mean? What does this mean? So this means that if I find or if I calculate the line integral of f along any two curves that have the same starting point and the same end point, then the two line integrals will be equal. Okay? So now let's suppose that the curve C is closed. Okay, so let C be a closed curve in D. Let C be a closed curve in D. Let C be a closed curve in D. We can sketch this. So let's quickly do a sketch of this. Let's sketch just a rough sketch. So let this rectangular shape be D. Let this represent the domain of f, which is D. Now inside of D, we have the closed curve C. So let this be the closed curve C. It's a smooth curve. So this is C. Okay, so C is a closed curve. Now, the next thing we do, let us take any 2 points on C. So let's take any 2 points. All right. Let's take any 2 points, A and B, on C. Okay, so let's take any 2 points, A and B, on C. Okay, so we take 2 points, A and B, so let this be B, and let this be A. So we just take any 2 points, A and B, on C. And then we let C1, okay, all right, we let C1, let's let C1 be a curve on C that starts at A and ends at B. In fact, let's take two curves. Let C1 and C2 be two curves on C that both starts at A, that start at A, okay, two curves that both start at A and end at B. Okay, so let's C1 and C2 be two curves on C that both start at A and end at B. All right, so now let's let this be C1 here, this yellow curve on C. Starts at A, ends at B. This is C1. Okay, and also we have C2. Also starts at A, ends at B. Okay, so this purple curve here, this is C2. That's C2 here. It starts at A also, and it ends at B also. All right, so that's our two curves here on C. Now, therefore, the line integral of f along this closed curve C is equal to the line integral along C1 plus the line integral of f along C2. But we must be careful here because of the orientation of the curve. We have to say minus C2 because we're calculating from A to B and then from B to A. So the curve C2 starts at A and ends at B, and the curve minus C2 starts at B and ends at A. So when we're calculating this line integral here, we have to do it in this way. The line integral of f along C is equal to the line integral of f along C1 plus the line integral of f along minus C2, which is the same thing as the line integral along C1 of f, of course, minus, so this integral here we can write it as minus the integral of f from C along C2. So we can write it like that. So we can say this is it's equal to this minus the line integral of f along C2. We can do like this. So now, since we assume that the line integral of f is path independent in D, and we have these two curves here, we have these two line integrals of this of f along these two curves, which start at the same point and end at the same point. This basically means that this is equal to 0, because this line integral here is exactly the same as this one, because we assume that f is path. We assumed that the line integral of f is path independent in D. So because these two curves C1 and C2 start at the same point and end at the same point, these two line integrals are equal to each other. So that's why we get 0 here, because we're subtracting two line integrals that are equal. So that leaves us with 0. Okay, so this of course proves the forward implication of theorem. Okay, so now let's look at the reverse implication of the proof. So now we start with the following. We suppose that, so now we start with the following. We suppose that the line integral of f along C is equal to 0 for any closed curve C in D. Okay, so let's suppose this. So we start here. So now let C be a closed curve in D. All right, let C be a closed curve in D. Let C be a closed curve in D. Let C be a closed curve in D. We can sketch this like we did before. Suppose that this is D here, the domain of f, and over here we have a C, closed curve C, an arbitrary closed curve C in D. Okay, so what's the next thing we do? We now divide C into two curves. Okay, or we can say this, let C1 and C2, similar to what we did before in the forward implication, we let C1 and C2 be two curves on C be curves on C that start at A and end at B. So let's C1 and C2 be curves on C that start at A and end at B. Okay, so let's just draw this. Suppose that this is B here, and this over here is A. Okay, and we've got two curves. Okay, let this be C1 again. It starts at A and it ends at B. Okay, it's a curve on C that starts at A here and ends ends at B. And we have another curve here, C2, which is also a curve that lies on C that starts at A and ends at B. Okay, there we go. So this over here is C2, and the yellow curve is, of course, C1. There we go. So these two curves, both of them make up the closed curve C. So suppose that we have that. Okay, now we say therefore, the line integral, well, first of all, we assume that this line integral of f along any closed curve C is equal to 0. In this case, obviously, C is a closed curve. We said let C be a closed curve in D. So because of our assumption, it's equal to 0. This line integral is equal to 0. So 0 is equal to this line integral of f along C. Now, this is equal to the following, though. Because we've divided C into two curves, C1 and C2, this line integral is equal to the line integral of f along C1 plus the line integral of f along minus C2. Okay? Now, again, this is the same as the following. It's the same as the line integral of f along C1 minus the line integral of f along C2. Okay? Now, because this difference is equal to 0, so this difference is equal to 0, because of our assumption, this obviously implies that if we subtract both sides, or if we add both sides by this line integral of f along C2, we get the following. We get that the line integral of f along C1 is equal to the line integral of f along C2. Okay? Which, of course, then proves that the line integral of f is path independent in D. Which proves that the line integral of f is path independent in D. So this implies that the line integral is path independent. Which then completes the proof.